Okay, so this problem is our final exercise related to the Euler's equations. As I showed the previous exercise, if we apply the Euler equation and we can understand where any point, how large the pressure at this point. Okay, so and another famous questions like the exercise showing here, usually we will have a tank, and a tank. This is an oil tank, and then if you just put the oil tank on site and there is no any shakings, so the oil in the tank is stable like the figure showing here. But sometimes we will have the earthquake happened. And when earthquake happened, and you can see for these questions, we have the horizontal acceleration is equal to 1.2 meter per second square. And this is the acceleration is equal to the seismic intensity is equal to 5. 就是我们说的震度。So this is the acceleration is equal to the earthquake seismic intensity 5. OK， 一般震度5就是会让你站的时候觉得会站不稳的那种摇晃的程度。如果你们有上工程地质的话，老师应该大概会说到。Okay, so and we actually know the oil, the SG specific gravity is equal to the 0.5. So we would like to estimate the pressures in the bottom of the tank. So we would like to estimate the how large the pressure at the bottom of the tank. So I just play one movie and you can understand how large for the intensity 5. So this movie, you see, that is kind of the shaking over intensity 6. So you can see the intensity 6, the shakings can just all of the structures in the house will be collapsed. Okay, so if you put your tank and put the oil in the tank and after the shaking, so you need to estimate how large the pressure at the bottom. So as I point out 2 points, the one point in here, the point B, and another point in here is the point A. And we know that the acceleration is the horizontal accelerations. So this is the acceleration we call that is the AX. Okay? But right now our liquid surface is along straight line directions. This is our straight line directions. Okay, so as I mentioned before, we apply the Euler's equation along the straight line directions. So we can try to put our government equation is the piezometric pressures. The piezometric pressure in here, maybe I put the number in left hand side. So we have the piezometric pressures and along the straight line directions. And the gradient is the minus will equal to the density multiply the accelerations along the straight line. So in our questions, we already know the horizontal acceleration, so we need to project the AX to the straight line directions. Okay, and we know that the theta angle in here. So we know we do the vertical line and project the AX to the straight line directions. Okay, so we know that the AS will equal to the AX and the cosine theta, right? And along this direction is the positive directions, S directions. Okay, and I highlight the point in here. This is the S1, the string line 1, and this is the string line 2. So we have the 2 point and string line 1 and string line 2, and we can expand the Euler equation in here. So we know that the minus piezometric pressure difference will equal to the constant density rho AS and ds, right? And similar to our previous exercise, we will do the integration both sides, and the point will from string line 1 to the string line 2, and here because there is along the string line, so the integration interval is string line 1 to the string line 2. So the point 1 here is the point 1 to the point 2. Okay, so we can expand the integrations. So in here we know that this is the minus, and the piezometric pressure we have the P2 plus the gamma Z2. This is a piezometric 2 at the point 2, and I keep the minus outside, and the inside here will become the positive. So this is P1 plus the gamma Z1. Okay, and the right hand side is equal to the rho AS, and this is the inside here is the string line 0.2 minus the string line 0.1. Okay, so in here we just try to organize the equations in here. So since we here, if you notice that here is connect to the atmospheres, here is the hole connect to the atmosphere. So we know that we don't have the pressure, right? So we don't have the gauge pressure will become the 0 because there is the open hole. So all of the environment systems connect to the atmosphere environment. So we don't have the gauge pressure in our questions. Okay, and then we know that the AS in here is equal to the AX cosine theta in here. Okay, so we can summarize the equations. So in here we know that the minus gamma Z2 plus gamma Z1 will equal to the rho AX cosine theta, and multiply the S string line 0.2 minus the string line 0.1. Okay, and we can have the take the gamma, and this will equal to the Z1 minus Z2, and equal to the rho AX cosine theta, string line point minus the string line 0.1. Okay, so we know that the gamma is equal to the rho G. So we can cancel out the low density. So and then I just summarize, and you can put the D1 minus D2 in here, and the right hand side we have the string line 2. We have the string line 2 minus the string line 1. Okay, and they will equal to, and I move the gamma to the right hand side. The gamma to the right hand side. So they will be equal to the AX divided G, and we still have the cosine theta, okay? And then you take a look for these problems. Z1, where is the Z1? The Z1 is in here. We have a Z1, okay? And the Z1 actually is the H1, okay? And the Z2 is the H2 in here, right? So we have the Z1, Z2, and it's equal to the length. It's equal to the length for the vertical difference. And where is the S1 minus S2 minus S1? Again, we have the straight line along the liquid surface. So you know that the D1 minus D2 divided S2 minus S1 is the sine theta, right? It's the sine theta. So this item is the sine theta. So we can reorganize the final equations. It will equal to the sine theta divided cosine theta. So we know that it is equal to like the tangent theta will equal to the AX G, right? The tangent theta will equal AX G. Okay. So this is our first questions, first equations. Okay, and then but our key question is we need to understand how the depths for the D1, D2, how the depths for the D1, D2, right? Okay, so and then if you see, I put the equation 1 in here. This is the tangent theta. It will equal to AX divided G. And if you don't have the tangent theta, and then we can rewrite the equation to here. We know that the D1 minus the D2 will equal to the AX divided G and the cosine theta multiply the S2 minus S1. And you know that the equation showing here, there is the cosine theta multiply S2 minus S1. S2 minus S1 is a line along the liquid surface, and we apply the cosine theta. They will equal to the L length, right? And then we know that how large of the L in here. Okay, so another equation we have in here, we know that the D1 minus D2 will equal to the AX divided G, and the cosine multiply the S2 minus S1 is equal to L. So we know that this is L, right? So this is our equation 2. We have the equation 2. But the key knowledge in here, we need to find out how large the D1, D2. But we only have the one equation, 2 variables. So it's impossible to know the D1 and the D2, right? So we still need another equations. Okay, so keep the equation in here. So we try to find out another equation. So another equation is, we know that the volumes inside the tank didn't change, right? If the oil flow outside, so the volume will change. But we assume the oil didn't flow out. So all of the volume inside will keep the same. Okay? So another government equations we have, we know that the 8 meters in here multiply the 40.4 meters, and we assume that the tank width is the same. So we don't know the width. W is the width of the tank. Okay? Will equal to, so the left hand side, the number in here is the volumes, the oil volumes. So after earthquake shakings, so we know that another volume is equal to the Z1 plus the D2, D1 plus the D2, multiply the L and divided the 2, right? It's an area for here. So the D1 plus the D2 multiply the L and divided the 2. So this is our third equations. We can summarize, reorganize, and multiply the W, right? But the width is the same, so we cancel out the width. And then we will know that another equation is D1 plus D2, and multiply 2 times, and add, and 4.4, and divided L. This is our another equations. Okay, so we have the two equations. We can try to find out the D1, D2, right? Right now, two equations and two variables, and we can understand how large it is. Okay, so we put a number for our questions. So the equation 2 in here, the Z1 minus D2 will equal to AX is the 1.2 meter second square, and the G is the 9.81 meter per second square, and the L is the 8. We have the 8 meter. So you can know that the number, use your calculator to calculate the number. 1.2 multiply 8 and divided 9.81. So it's equal to the 0.978 meter. This is the equation. And another is we have the equation 3. We know that the D1 plus the D2 will equal to the, you use your calculator, the equation showing here. So you can compute the number. So the 2 multiply 8 and multiply 4.4 and divided the 8. Okay, so it equal to the around the 8.8 meter. Okay, so and divided 2 and 8. Okay, so you can you have the two equations. So maybe this equation is the 4 and this equation is the 5. So you know that if we have the 4 plus the 5, and we can cancel out the D2. So 2 times D1 will equal to 9.978. Well, will equal to the 9.778. So you know the Z1, how large is the Z1, divided the 2. So it's around the 4.89 meter. And you can put the D1 into the equation 4 or equation 5. And you know that the D2 is the 3.91 meter. Okay, so since we already know how the depths for the Z1, D2, and we just based on the hydrostatic equations in here, we have the gamma oil, and we have the D1, D2. So we can compute how large the pressure we have. How large the pressure we have at the bottoms of the tank. Okay, so the question is a little bit complicated, but we know that we have the Euler equations, and we have the acceleration, so we can estimate the pressure at any point on the tank. Okay, just based on the Euler's equations. Okay, so you have the number, so I don't calculate how large the pressure we have. You just follow the hydrostatic equation showing here. Okay, we have the hydrostatic equation, so you can directly to compute how large the pressure we have. But the key knowledge in here, we need to know the depth above the point B and A. If we don't know the depth, we cannot calculate the pressure at the bottom. Okay, so that is the idea for the Euler's equation. This is very important. The exercise is very important. Okay, so if you design the height in here is not large enough, so when the earthquake shaking happens, your oil will flow out, right? If the height is not large enough, the oil will flow out. OK， 这个问题很严重，就是我们一般都觉得不会有地震，所以我们设计卡车载油就这样子载嘛。可是如果你当它在行进的过程中有地震发生的话，那油就有可能会怎么样？就会外漏。OK， 所以我们在设计上一开始这个高度跟这个体积就要算好，你要能够去承受。一般你可能在开车的时候突然有来一个大地震发生的话，万一油漏出去的是一件当然不好的事，但如果是有毒的液体出去，那就是更夸张哦。所以在工程设计上，不是说我们看现在这个样子 OK 就 OK， 我们必须要去设计它可以承受多少的加速度的变化。OK， so this is one final exercise for the Euler's equations. So we move to the next. It's a very important equation in this chapter. We call that the Bernoulli equations. Okay, and this is we just apply the Bernoulli equations, derive the Bernoulli equation along the straight line. Okay, so the idea, again, we have, what do we have? We have the Euler's equations. And since I say we only focus on the Bernoulli equations along the straight line, so you see that the differential is along the straight line, and the accelerations here is along the tangents accelerations. Okay, so two assumptions is very important. One is we assume the steady flow, and another we think our flow is in viscid flow. That means the viscosity effect is in our problem we don't consider the viscosity effect. Okay, so for these questions we know that what is the AT. The T is the tangents accelerations along the straight line. So as I mentioned before, we have the two acceleration terms. One is the convective. So we have the dv along the straight line and multiply the v, and the plus the dv dt, right? And the first item we call that the convective acceleration, and the second item we call the local accelerations. And if you notice that we assume the flow is a steady flow, so that indicates we don't have the velocity didn't change with the time. So we don't have the items for this part. We don't have a local acceleration because we consider our flow condition is steady flow. When we notice that the steady flow, that indicates the physical parameter didn't change with the time. So any differential with the time, we don't have we don't have this effect. So we cancel out the velocity change with the time items. So we just put the number in here. We know that the piezometric pressure along the straight line So we have the P plus the gamma Z, and we have the density, okay? But right now the AT, we only have the V dV ds, right? We only have a dV ds. And then if we notice, we focus on the V dV ds, we can do the integrations by part. So we put the velocity go inside. So we can rewrite the equation will be the 2 over v squared, right? Because we put the velocity outside and to inside the differential with the straight line. So we can, because we do the integration, so the v will become the v squared, and we have additional constant value 2 outside. Okay, so we can also rewrite here we have to be the rho multiply the dv squared and the ds and divided the 2, and then we consider aside when we derive the Euler's equation, we have very important assumption is our flow is incompressible flow. So the density always the constant, right? The density is always a constant because the flow is uncompressible flow. Okay, so because we assume the flow is incompressible flow, so we can put the density inside. So it will be a rho v squared divided the 2. Okay, so both sides we have a differential along the straight line. We have a differential along the straight line. So we can put them together. So we rewrite the equations. We know that the ds and the inside is the P plus the gamma Z plus the rho v squared divided the 2, and it will equal to the 0. Any parameters differential with the straight line will be the 0. That indicates the piezometric pressures plus the 2 over rho v squared will always the constant value. Because the constant value do the integration with the straight line will equal to 0. So this item is always the constant values. So the first item here is the piezometric, and the final here is parameter associated with the velocities. Okay, so the Bernoulli equation tells us if your flow, your flow is the steady flow. Okay, the very important assumptions, and because we start from the Euler's equation. Euler's equation tells us it's an implicit flow. That indicates the viscosity is not important. Okay, and the Euler's equation tells us one important assumption is the incompressible flow. Okay. 所以就是稳态的流体，然后不可压缩流，然后又非粘滞流。Okay, so the Bernoulli equation need to satisfy the 3 assumptions. Okay, the steady flow, inviscid flow, and the incompressible flow. If the assumption is satisfied, and then we can say that along the straight line, you just pick up any 2 points. So we pick up any 2 points. Always satisfy the Bernoulli equations. Always satisfy Bernoulli equations. So that indicates the P1 pressure here plus the gamma Z1 plus the 2 over rho V2 squared will always equal to the point 2 P2 plus the gamma Z2 plus the rho V, sorry, here is 1, So the V2 square divided 2. Okay. So the idea is very simple. We just pick out the 2 points along the same straight line. And the 2 points will always satisfy the Bernoulli equations. What's the Bernoulli equation? The Bernoulli equation tells us very important ideas is a piezometric plus the 2 over log V squared always equal to constants. But only satisfy the 2 points located at the same straight line. If not, you cannot apply the Bernoulli equation. 只能用在2个点是在同一条流线上，目前是这个样子。那你就可以用 Bernoulli equation 去了解一些现象，这样子。Okay, so this is the idea. So the following slide just tell us what's the physical meanings. So the first physical meaning for the Bernoulli equation, we call that the energy is conserved. So the energy conservation, why we can say that? Because you see, the first item, this item, what are the item for the P? This is a different formula for the Bernoulli equation, because the original we have the P plus the gamma Z and the plus the 2 over log V squared, right? And always equal to constant. And then both sides we divided the gamma, so we have the P divided gamma and the plus the Z. And there is 2G V squared. But always equal to the constant 1, and there is the constant 2. And this is a header form. We use the head form. And this is for the pressure form. So different representation, but they are the Bernoulli equation. Okay, so and we go back to see the Bernoulli equation with the head form. So the first one is here. This is we call that the work. The work caused by the pressure force. Okay, and what is the Z? Z we call that this is the potential related to the potential energy. And the final one is the V. V is clearly, it is the kinematic energy, right? So that's why we can tell you the work caused by the pressure force plus the potential energy and the plus the kinematic energy always constant. Your sum of the energy is always the constant. So that indicates the energy is conservation. Okay? And usually we combine two items, the P divided gamma plus Z, we call that the piezometric head. And we have the final one, we call that the velocity head. It's related to the 2G over V squared. Okay? So we always assume the constant, the energy is conservation. So there is no any energy loss, right? Okay, but in real case, in practical, it's not always satisfied, because we know if we have the frictional force and the energy will dissipation, right? Dissipation with the heart will dissipate. But in here, there is no frictions, because we assume the fluid is in viscid flow, no viscosity, so we don't have the frictional force. So that's why the energy will conservation. OK， 所以这个观念蛮重要。我们这里假设就是能量会守恒的原因，是因为我们说没有粘滞力。那我们之前一直强调粘滞力不就是流体里面的摩擦力吗？所以你没有摩擦力，其实能量就不会用热的方式去消散掉。那我们知道热是抓不回来的，所以能量那个有热的摩擦，能量是不会守恒的，它是会消散掉的。 OK， 所以我们在伯努利定律里面才可以用能量守恒的概念去说伯努利定律。Okay, so this is a very important idea. Okay, so how the applications for the Bernoulli, as you can see, this is we call that the static pressure tube. As indicated, we have the pipe, and the pipe there are some flow, and we make the hole in here, and we at the hole we put the tube, we put the manometer tube, and how large the pressures at location A, it indicates the deflection height, how large the deflection height in here. So as you can see that the question tells you the static pressure is given by the PA is equal to the gamma delta Z. The gamma delta Z. So we can use the deflection height to predict the pressures at the location A. So the topic in here, we would like to tell you how to measure the velocity and the pressures at the fluid particle. Okay? And this is another case. If you notice that we have the baseline, this is the baseline. Okay, we have the baseline, and this is we suggest we think the baseline the Z is 0, and we have the total height. The top we have the total height, and we put the nano. This is a nano pipe, and we know that the nano. If we start from the right hand side to left hand side to the right hand side, the elevation will increase. So you see the elevation increase. So we have a Z1, Z2, and the Z3 will increase, right? And then, but in here, what is the velocity? We have the velocity V1 and the V2 and the V3. So where is the largest one? You see the V2 is the largest one. So we have the velocity height. We have the largest velocity height. But we have the small pressures in here. So in previous exercise, I always emphasize if the lower pressure, why the lower pressure will happen? Because the velocity at the regions will increase a lot. So you see the case, the velocity increase a lot, and the pressure will decrease. So high velocity speeds will have the lower pressures, and we afraid the lower pressure environment because the liquid will become a vapor, and we have the cavitation phenomena. 我们之前有说到，只要有高速带就会有低压的环境，然后我们会非常害怕那个低压的环境，因为液体会气化，液体气化以后就会形成 bubble 去破坏结构物的表面，然后我们说那个叫血蚀现象。Okay, so this is one idea, but even though the velocity will change and the pressure also change, but the final total height always the constant. The final total height always the constant. So this is, we call that the Bernoulli equations. The Bernoulli equations. Okay? So we have the one exercise. And then we finish the exercise and we can finish our class today. So the same, you can see we have the baseline. This is our baseline. And we only know we have only two informations. Is the deflection height is the 1 meters, and another deflection height in here is a 0.5 meters. Okay, and we have the straight line, so I plot the straight line in here, and I put the point. Maybe this is the point. This is my point 1, and then in here, this is point 2. So we have the point 1 in here, and we have the 0.2 in here. And if you take a look, the equation tells you the fluid inside is incompressible fluid. Okay, and we only know two parameters. The diffraction height is one is 1 meter, another is 0.5 meter, and we know that the velocity in the throat section is twice as large as in the approach sections. So that indicates the V2 velocity. There is the V2, right? The velocity in here. There is the V1. We only know that the condition is V2 is 2 times of the V1. Okay, this is our conditions. So we assume the fluid is incompressible and a steady flow. So it is satisfy the Bernoulli equation. So we know that the P1 multiply plus the gamma Z1 plus the 2 over rho V1 square will equal to the P2 plus the gamma Z2 and the plus the 2 over rho V2 square. Okay, and what's the problem? We need to answer the problem found the velocity in the throat sections. So the question is our target is the V2, how large it is. Okay, so based on this equation, we know that this is the items. This is item for the piezometric pressures at the location 1. And this is piezometric pressure at the location 2. Okay, and so we do some reorganize the equations. So we know that the piezometric 1 pressures multiply the piezometric pressure 2 point is equal to 2 over rho, and there is the V2 square minus the V1 square. Okay, and if both sides we divided the gamma, both sides we divided the gamma. So here is a piezometric 1 minus piezometric 2 pressure 2, and divided the gamma. We don't know what the liquid. The exercise only tells us that it is the liquid. Okay, but we don't know what kind of liquid. So I put the gamma in here, and there we divided the gamma and the rho, and there is a V2 square, and we know that the V1, the relationship between the V2 V1. Okay, so we know that there is 4 over V2 square, right? Because we follow the equation in here and replace the V1 by the 2 over V2. Okay, and then you see the item for here is equal to the piezometric head H, the HZ1 minus the HZ2, piezometric head 1 and 2 minus, okay, will equal to, there's a gamma is a rho G, so it's a 2G over 1, and we take the V2 square outside, and the inside is only equal to the 1 minus 4 over 1. So it's equal to the 2G over V2 square multiply the 3 divided the 4. Okay, and we know that the piezometric head HZ1 is the 1 meter, right? 1 meter in here, and minus the piezometric head is 0.5 in here. Okay, will equal to the 2 times gravity 9.81, and we don't know the V2 square, and multiply the 3 divided the 4. So we can summarize the V2 square will equal to, you can use your calculator. So I use my calculator to compute the answer. It's around the 13.08, and you take a root. You take a root of the V2 velocity square, and the V2 will equal to 3.62 meter per second. Okay, so this is our final answers. Okay, so this is one exercise tell us how can we apply the Bernoulli equations. So you need to double check the condition is satisfied or not. So the condition most important already know the incompressible flow in here. OK， 好，那所以大家要小心这个题目，就是有些条件要先试用以后，你才可以去用白努力方程这样子。那今天的重点就是同一条流线上的任意2点，它的 piezometric 测压压力的总和加上速度项的压力一定会等于常数，所以只是加减减，然后做一个平衡，你就可以知道说，那在不同位置上的流速是多少。所以伯努利的重点是让我们去推流速比较多，就是任何一个位置的流速是多少。如果你已经知道它的测压压力的头，那这里就跟你讲 H1、H2 等于多少这样子。OK， 那我们今天就上到这里。